Уважаеми колеги, тази година отчетната сесия на секция Алгебра и логика протича малко разпределено във времето. Поради големия брой членове на секцията, вместо в един ден решихме да разделим докладите на отделни семинарни доклади и един ден на обявената дата. Доцент Веселин Филев реши да използва тази възможност, както и много други наши колеги. Това е неговия годишен отчетен доклад. Веско, заповядай.
Ами, благодаря. Аз, както говорихме преди малко, ще мина на английски, тъй като има не българско говорящи хора. So the title of my talk is AdS CFT Correspondence, Metropolis-Hastings Algorithm and Generative Adversarial Networks. Now, the main, the most interesting thing here is probably the Generative Adversarial Networks, GANs, also famous, and that's the thing that I'm going to just mention at the end. But the Metropolis-Hastings algorithm is, it's what usually people understand when they do Monte Carlo simulations in physics. Usually that one is used. So I'm going to go in, given that all of the audience is mathematicians, I'm just going to even present a few theorems, which is probably unusual for a physics talk. Now, in the first part of the talk, I'm going to talk about the AdS CFT correspondence, which sets the context of the talk. It is, where I'm going to explain what it is. I mean, I have explained this last year, so it's not going to be different, this part. And then there was a recent paper. Well, it's not that recent. It was published during the summer, but yeah, it's from this year, about the D0, D4 backreacted system. I've been talking about this system for a couple of years now, so now it's finally published. And the motivation to study this system comes from the fact that it is dual to the Berkooz-Douglas matrix model, which, on the other hand, can be used to study the AdS CFT correspondence in this non-supersymmetric, well, although in this case, the background is supersymmetric, but you can break that one. So in this lower dimensional version, and you can actually simulate it on a computer. But simulating it on a computer in the context of the large N limit, where the AdS CFT correspondence works, requires very large size matrices. And there is a well-known problem with this kind of simulations, that it takes a lot of time for the system to thermalize. So that's why I'm going to clarify the Metropolis-Hastings algorithm. I always mention some simulation in my talks. I never discuss how this is done. So I'm going to now talk about Markov chains, the Metropolis-Hastings algorithm, and how we simulate physical systems using that, the problem of thermalization, and how we can use GANs, generative adversarial networks, which are artificial neural networks, to improve the thermalization of this algorithm. Now, this last part is work under progress. I only did some preliminary work, so I'm going to just report some preliminary results there. Now, the AdS CFT correspondence, as originally proposed by Maldacena years ago, more than 20 years now, is a correspondence between type 2B string theory on the background of AdS 5 crosses 5 spacetime and N equal 4 super Young-Mills. Now, but the thing is, it works in the large N limit. You have to consider the so-called Hooft limit. When you take very large size of the matrices, the color degree of freedom, which is the size of the matrix, and you expand the Feynman diagrams, and then one can see that in this limit, only planar diagrams survive. So this is kind of like a planar limit. And it works even for QCD, which is N equal 3. So even for N equal 3, you can do 1/33 expansion. So that was the original idea by Hooft, and I think he got Nobel Prize around this idea. I'm not sure if he got it exactly for that, but maybe for that. And so this is the context in which this correspondence works. And the way it works is it uses this AdS CFT dictionary. This is the formula proposed by Gupser, Klebanov, and Polakov and Witten. So you have on the left-hand side the generating function of the dual conformal field theory, which is just your partition function with some sources. And on the right-hand side, you have, like the a representative of these sources and the tree-level partition function of supergravity. String theory, but at this level it becomes supergravity. And the idea is that you can use actually perturbative calculations on the supergravity side, where you just do supergravity in the probe approximation, for example. Although it doesn't have to be in the probe approximation, but it's weakly coupled interactions that you study this way. And you can transfer the result into the strongly coupled dual theory. That was the hope and the main application of the AdS CFT correspondence. And now what we are actually going to discuss is generalization of the AdS CFT correspondence to include flavor degrees of freedom. Now, the original formulation of the AdS CFT correspondence is built on studying D-branes, which are, D3 branes, that's the idea. And the D3 branes are dual to n equal 4 super-Young-Mills, and in particular, these strings that are connecting the D3 brane to itself. Actually, it's a stack of D3 branes, NC, the same number of D3 branes as the size of the matrix. And you can even think that the matrix actually labels the beginning and end of a string that is beginning from one of the branes and ending on the other brane. So that's how you can think about the connection between string theory and gauge theory arises, is because these are called Chant pattern factors. So you can have this, you can parameterize the short strings in this way. Using where they start and where they end, and when you look at the low energy limit, what will arise from there is n equal 4 super-Young-Mills. Now, to add flavors in this picture, why flavors? Well, we're built out of flavors. Baryonic matter is flavor in the standard model. So, and for that we add additional stack of branes, the D7 branes, and then these long strings that are stretched between the D3 and D7 branes. They correspond to the flavor degrees of freedom. One of the index, the one that ends on the D7 brane, becomes now a global index, kind of like it becomes the global flavor symmetry. The other is just the single index that participates in the fundamental representation of the gauge group. Okay, and I should say that the gauge fields, they transform in the adjoint representation. Now, the string stretch between the D3 and D7 branes corresponds to the mass. And there is this correspondence between these two theories. And in this way, you can actually introduce flavors. And now the nice thing is that you know that the mass of the flavors is dual to the condensate. And knowing that the mass corresponds to the separation of the D3, D7 branes, this will give you a parameter that you can use as a source in order to calculate the condensate of the theory. And there is supersymmetry in the picture. It simplifies things in the sense that it limits a lot the freedom and the possible gauge theories that you can write to couple this system. For n equal 4, it uniquely determines it now. And there is a unique way to couple n equal 4 super-Young-Mills to n equal 2 hypermultiplet. So it's not a huge surprise that this system is actually dual to that other system because they have shared the same symmetries. Now, but it's not just symmetry, of course. They're dynamically equivalent. That's the statement here. And now, what I'm going to talk about actually is a lower dimensional version of this, because what we wanted to do, like years ago with Denjo, we started this, is to start running simulations to test the AdS CFT in the strong coupled limit. We're not, of course, the first one to try to do that. But in this case, in the case of these systems, we are, and we are with flavors. And the idea was there were a lot of accumulated papers with flavors, and they have some theoretical complications there. And we wanted to see it working. Now, the idea is the lower dimensional version. Why lower dimensional? Because if you want to simulate a higher dimensional gauge theory, first you have the problem of space-time. You have to discretize it, but that is handled. But the main problem here is supersymmetry, because to put the supersymmetry on the lattice, it's very challenging. There is one group, there are actually two groups that are related that try to do that, but it's very difficult. And the reason is for the so-called fine-tuning problem. So the thing is, when you put the theory, gauge theory on a lattice, you discretize the theory. And then naively, when you write down the discrete Lagrangian and you take the limit of zero size of the lattice, it seems that the Lagrangian is the same. But this is a classical limit. Now, if you put that in the partition function, as a mathematician, you can think about taking the limit within the continuous integral, and that doesn't work so smoothly most of the time because there are so-called radiative corrections that are generated. You need to cancel them. You need to regularize the theory, and for that you actually usually need analytic control. You need to be able to analytically cancel these terms. Numerically canceling them is like numerically searching a huge space for a single point, and that's the fine-tuning problem in this case. And that's why it doesn't work it cannot be done in this way. The way people do it is they embed the theory in with some global symmetries. The N=4 super Young mills can be constructed that way. You construct some highly symmetric lattice, and these discrete symmetries, you argue, will abolish or inhibit, prohibit most of the counter terms that you can think of. Most of the terms that can arise in renormalization, and that's why that's the whole. But this is a very specific case. In general, it's not possible. And however, in one dimension, there is a theorem that it is possible. The theorem just says that there are no divergences in the renormalization, and because of that, you don't have to worry. It's super normalizable, the one-dimensional theory, so you can actually trust that the classical limit will reproduce the quantum limit, and just putting the theory on a lattice and taking the small size lattice limit you will approach the actual physics, not some physics governed by artifacts. And for that, we needed to lower the dimension. Lowering the dimension, you look at the T-dual to the D3D7 system. There is a so-called notion of T-duality in string theory. And so this is like a lower dimensional analog, like your 1 + 3-dimensional field theory now becomes 1-dimensional quantum mechanics, and the analog of the flavor D7 brains are now flavor D4 brains. This model, by the way, was proposed by Berkooz and Douglas as a generalization of the BFSS matrix model. And the idea was to introduce M5 brain density to the Berkooz-Douglas matrix model, but it's also dual to the D0, D4 setup. And now the idea is that we simulate this model, we compare with the supergravity calculation, and we check AdS CFT. And we did that like years ago, like 5, 6, 7, between 5, and it worked, but it was in the so-called probe approximation, which is okay, but we said, well, we have to go beyond. You have to do you have to treat the flavor brains as, so in the probe approximation, you treat the flavor brains as probes in the geometry set by the D0 brains. What you want now is to take the back reaction and construct a new background, the D0, D4 geometry. And I've been talking before about this, how you can do it. And the idea has been around. The reason why it wasn't completed in the literature is because it cannot be done fully analytically. I think that's the reason why. Not that it was such a big secret, I guess, and probably not enough motivation to do it because, we have this motivation with the AdS CFT and the Berkooz-Douglas matrix model. Now, the way to do it is very nice, very geometrical. So you take, first of all, the D0, D4 brains, they live in 10 dimensions, but they come from 11 dimensions. If you go to 11-dimensional gravity, you can understand the D0 brain as a Kaluza-Klein compactification from 11-dimensional spinning, geometry with a spin, geometry with the angular momentum. The D4 brain can be understood as compactification of M5 brain, or given that we start from 10 dimension, we call this uplift. So we uplift the D0 brane to Kautz-Klein momentum in 11 dimensions, and the D4 brane, we uplift it to M5 brane. And now we use something called Garfinkel-Vachaspati construction, which allows you to construct one geometry from another by deforming it in a particular way. Now the idea is it is valid for this theories with this action, and as you can see, this includes gravity with some additional fields. So this is good enough for us, and because supergravity has the first term, the Hilbert-Einstein action term, which is just the Ricci scalar curvature entering there, and the last terms with the Ramon fields that is in 10 dimensions. In 11 dimensions, it's even simpler. It has just one form. And the idea here is to start with this theories and then consider something called hypersurface orthogonal killing field. So it's a killing vector with the zero norm. And the hypersurface orthogonal condition is the third condition here, where S is some scalar. And then if you have this, then you can construct the following deformation of the metric, and you claim that first that these conditions are true, and the second condition is in fact enough that it's a solution to the claim is that it's a solution to the equations of motion generated from the action above. But in addition, this field psi here should satisfy these properties. It should be a harmonic field, and it should be, well, its derivative along the killing field should be zero. Now, so let's see how this works in flat space. Well, we start with the flat space in 11-dimensional gravity, and we're going to see that this will produce the GA construction, which is Garfinkel-Vachaspati construction, will generate for us the uplift of the D0 brane geometry. So you go to light coordinates. This is just flat space. You rewrite your space-time in flat coordinates, and then you use the killing field associated to translations along X1, X11 is hypersurface orthogonal killing field. S is 0. You can show that it satisfies it with S equals 0, meaning that that it is just true that this is equal to 0. And then psi is equal to hash, which is just renaming, because hash, H is the usual choice of for the scalar in this family of metrics. And now if you perturb the flat space with this, you get the following background. And this background is exactly the uplift of 11-dimensional uplift of D0 brane geometry. If you do a compactification to 10 dimensions, you're going to get the D0 brane geometry. So we started with flat space, and we generated with this GA construction the D0 brane geometry. Now the idea is, well, don't start with flat space. Start with M5 brane space, membrane space, and use the same construction to generate within this, to deform this background to the one that has also the uplift of the D0 brane. And the claim is then this is the uplift of the D0 D4 brane geometry. And so the M5 brane geometry is the uplift of the D4 brane geometry. You have the same flat sector here, and you focus on this flat sector here. You introduce light cone coordinates, and you do exactly the same argument. You use the same killing field, you add the same deformation, and you obtain that metric. And that metric is the deformed metric. Now, okay, very nice. Not that you had to do it that way. You could just solve the supergravity equations. It would still work. It gives exactly the same result. And in 10 dimensions, you get the following equations. Now, the thing is, this is not a solution yet, because you don't know this function, h of u and v. You don't know it yet. In general, it's any harmonic functions function in this transfer space. It doesn't have to be just depending on U and V. U here is the radial. Well, you break here the 11-dimensional space in a sense to time, and then you have the x11, then you have R4, and then you have R5. And this R4 and R5 have radial coordinates in them, and U and V are the radial coordinates, as one can see here from the matrix here. For the metric here, this is like spherical. Well, yeah, these are like spherical coordinates in this R4, and these are spherical coordinates in R5. Now, so the next is part of the talk is about solving, well, not to the rest, but just a few more slides about solving for this H of U. So H of U satisfies this equation of motion, which is actually a harmonic equation, but with this, with this additional term here, right? Because of the M5 branes. And you can actually obtain this by using conservation of angular momentum. Even that is enough to use it. Or you could reduce to 10 dimensions and use the Einstein equations. It's going to give you the same result, the same equation. Yeah. Actually, this is already from the GA prescription. Sorry, this is from the GA prescription. And you can get it from Einstein equations in 10 dimensions, and you can also get it as angular momentum conservation condition in 11 dimensions. And now the idea is to look at the solution that is, well, the localized solution is the following. You have the D0 branes and you have the D4 branes separated from them at some distance in the transverse R5. So this is a 5-dimensional Euclidean space, which we imagine here, and this is the radial coordinate in it. And in this space, there is a point through which the D4 branes go. Now, this is more difficult to do. What we do instead is we partly smear the D3 branes, the D4 branes. We say, well, consider a cylindrical shell. So put them on a shell in this R4. Why do I call it cylindrical? Because the full space is in this R5, sorry, is 11-dimensional. So it's not that it's a fully spherical. They have this extra component. This is like the radial coordinate in the R4, which kind of you can think of it as giving you the length of the cylinder. It's not cylinder in real space also, but in this picture is a cylinder. And this is the kind of solution that we're looking for. So it still depends on U and V. It still depends on U and V. It's just, it doesn't depend on the angular coordinates in R5. Now, to obtain a non-perturbative solution, you need boundary conditions. And this we impose by actually using the fact that when we put the D-branes on a shell, inside the shell, there is the analog of this Birkhoff's theorem, which is also a theorem. And which says that inside this spherical shell, the solution will be as if there are no D4 branes. But of course, it's not, there are still some constants to be fixed. And these constants you fix by saying that you want the solution to be smooth. Well, not smooth actually, but continuous across the shell. There is some surface, there could be some small delta function sitting there. So it may not be smooth, but, oh, sorry, there is a comment. I cannot see the comment though. There is no sound. There is sound, right, guys?
No, there is sound. Maybe this is local.
No. 20 minutes in the talk, I was really shocked.
We hear you, don't worry.
Okay. Sorry. Yeah. Good. Now, right. So this is similar to Birkhoff's theorem in Newtonian gravity, and you can fix this constants. You do that in Fourier space. You Fourier transform, but these are just details. The thing is, you can see that inside, the solution inside can be written that way. So you can deform the flat metric. It's even a reparametrization of flat space, if you wish, inside the shell to look like that. It's not flat, right? It's the D0 background. So you have the D0 background, and you kind of it has a spherical. The original D0 background has a spherical symmetry. Now, when you put this cylinder here, you now have like an axial symmetry. And inside the shell, however, inside the cylinder, you don't see the D4 branes. So it seems that it was just your coordinates that broke symmetry, and you restore this by using another set of coordinates, these coordinates, and you can write this to look like spherically symmetric one. And then you say, well, okay, then I look at the most symmetric solution in this the symmetric coordinates, and it's that one. Now, if you go back to the original coordinates, you see that the solution actually has no axial symmetry. So you found no spherical symmetry. So you found a non-spherically symmetric solution, which exists, obviously, of the D0 brane background. And now you use that one to actually source the solution outside of the shell. And then you go to Fourier. These are details. I'm going to go a bit briefly through them. So you take this Fourier transformation, then the equation of motion that I wrote becomes this equation of motion. Now, this equation of motion, although innocently looking, doesn't have analytic solutions, unfortunately, which is the reason why it wasn't probably published before this result. And then you have various approaches. Now, what can you do? Well, you can try to do a perturbative expansion. You do this perturbative expansion. So V4 is kind of like related to it's a parameter in the D4 brane geometry. In a sense, it's proportional to the ratio of number of D4 branes and number of D0 branes, and V0 is the shell that we introduced. And if you expand, you can get this perturbative solution to first order. I wrote it there. You can write it to any order, but you cannot solve analytically for all the components after some order. And now you can also do a numeric calculation, and we did that. It's in the paper from the summer, but I'm not gonna construct report the numerical solution here. Now, the hope here is that you are gonna, next you're gonna take this background, you're gonna add temperature to it, and then it's gonna be dual to the study that we did already 6 years ago, but in the quenched limit, and you're gonna see probably a slight improvement in the agreement between AdS CFT and so the results on gravity side and in simulations. But at this point, I will say that was the motivation, and we need large N simulation to be able to capture this. And now I'm going to switch and start talking about simulations. So I'm going to start talking about Markov chains now. So what is a Markov chain? It's just a discrete sequence of random variables, you can think of it. It's just a process, and the main thing, the reason why we call it Markov chain is because it satisfies the Markov property. Now, so there is the notion of Monte Carlo time, which is just that as your discrete process evolves, you label each state of the process as a time. This is your Monte Carlo time. And at time tn, the system, the state xtn, can be in one of a finite set of possible states. It doesn't have to be finite actually, but we restrict ourselves to the finite. So it can be one of these states, and this is called the state space. Now the Markov property is that the probability of being in a particular state Zj at time tn plus 1 depends only on the state at the current time. So your next state depends only in your current state. It doesn't depend on the previous, the one before the previous. It's just this. It's also called a memoryless process, stochastic process. And this with another just another condition defines martingales, by the way, which are useful, widely used in quantitative finance. But we don't have a martingale here. It's just that the next state depends on the current state. And now another very important Denjo is here. Hi, Denjo. So the thing is, I just started talking about this transition.
Yeah.
So the important property of the Markov chains is the so-called transition matrix. So let's look at some initial probability distribution. So this pi 0 ji is the probability that at time 0 the chain is in a state zi. This probability vector represents your initial distribution of the chain, and the only other parameter of the chain that you have is the transition probability, which is the probability which is Pij, and it's the probability for transition from state Zi at time Tn to state Zj. But this comment here at time Tn actually is not that relevant because we require that these transition probabilities are constant. So we require that the transition matrix do not depend on time. And if we organize the transition probabilities in a matrix, they give us this transition matrix. And now, as you can probably see that I'm sure you can see that the sum of the rows should be 1, because this is actually, which means you start with the given state and then you have to go, you have no other choice but at the next stage, you will arrive at one of the other n minus 1 states or the same state. And therefore, the sum of these probabilities should be 1. So sum over I of Pij is 1. So the sum of the entries in this matrix is 1. And then, given that they do not depend on time, then the transition from time Tn to time Tn plus k is just the matrix to the power of k and ij component. And this is all you need. And with this initial probability distribution and the transition matrix, you can actually evolve the Markov chain. Now, and there are various Markov chains, as you can imagine, and here we're going to be interested in the so-called ergodic chains. They're also called regular chains, but I like the word ergodic, sounds more fancy. It's fancier. So the first property that we want is the so-called irreducibility. So a Markov chain is irreducible if for every pair of states there is a finite number n, such that after n steps you go to step zj, you transition to zj, and you can see how this relates to ergodic, right? Because it means there are no disconnected components of the chain. So like no matter in which state you are, after sufficient amount of time, you will go through all possible states. And mathematically, this is actually it can be expressed in not in a difficult way. Now, the period of a state, this is a little bit counterintuitive. So the period of a state is the it's the period such that if you are in a state Zi, after d repetitions, you repeat to only after multiple of d times. And d is the largest number with this property. So this is a little bit, but it's the largest number of this property. And then a state is aperiodic if it occurs at every step. That is, it has a period d equal 1. And for irreducible chain, all states can be shown to have the same period. And you can see that the condition to be aperiodic, a given state to be aperiodic, is just that the component PII is non-zero. There is non-zero probability that it will be again in that state. And so ergodicity is that the Markov chain is both irreducible and aperiodic, and it's called ergodic. So, and also a regular chain. So these are the chains that we're interested in. And it's going to become very clear why we're interested in these chains mainly. Well, first of all, let's talk about stationarity and convergence. So a vector of probability is Pi, which is just the probability that you are at some time Tn, let's say, in state I. Well, it is called stationary if it satisfies the following condition here. Now, it is understood where this comes from. Like this just means that it remains the same, that the probability to be in a state J after one Monte Carlo step is the same as before. And so it's stationary. And this is called global balance condition. Now, if a Markov chain is irreducible, it has a stationary distribution and it's unique. That's a very nice property. So if it's irreducible, it has a stationary distribution and it's unique. And then if it is ergodic, it doesn't matter where you start from. The final state will be independent of the initial state and will be the stationary distribution. So it converges to the stationary distribution no matter where you start from for ergodic chain. And that means after sufficient number of repetitions, well, n infinity, the transition matrix will look just like the rows will be the components of the stationary distribution. So this is what we have here as a condition. Now, and these are theorems, which obviously we're not going to prove. Well, there is also the so-called detailed balance condition. I think it's important. I think the name comes from chemical reactions. And it is called that the Markov chain is reversible if it satisfies the so-called detailed balance condition. Now, what this means really is that the total probability to transition from state I to state J is the same as the probability to transition from state J to state I. And I think that's why it's called balance, because like if you have a chemical reaction, it means the substances are in balance, maybe. Now using this property of the transition matrix, it's very easy to see that this actually implies global balance. That if a distribution satisfies the detailed balance condition, it is stationary. You just sum over I here on one side. Here, let's say. And on the other side, you're gonna get, I think, J or something like that. Yeah. Okay. Now, yeah.
So there is this balance of indices in this equation.
Sorry?
Is this equation good with respect to indices?
Yes, it is.
I think you need to use that sum over I of PJI is delta.
Sorry?
If you sum over I on the right-hand side, you get 1 for, unless the column is, you get 1 for the column I. So it gives you, it balances.
Yeah. It's just that I'm thinking, I don't know why I stopped at this. I think I might have flipped some index, or maybe because I'm presenting. What am I saying? That I have to sum over the first index. Yeah, maybe let me look. I think I have to sum over the second index. That's the thing. This should be sum over.
Vesko, this is I think pretty much common knowledge stuff. We know about this. So you can
Yeah, okay, it
skip
doesn't
the
matter.
details, move on
stuff,
to what you are doing with this. Yeah.
Well, I didn't know. Okay, now it should be J here. Okay, that's the thing. Then it works. Now, so the goal is to construct a Markov chain. So I didn't know that everyone is such a big specialist in Metropolis-Hastings algorithms here.
Not the algorithm, but just Markov chains. I mean the basics about regular Markov chains.
Sure.
Yeah.
Well, but I'm not sure the detailed balance is.
But from that point on, I admit I'm not a specialist at all. So please switch to full detail after the.
I think this is already the point for full details, but doesn't matter. It's the same.
Right.
Okay. So this should be J here. Okay. So the goal is to construct a Markov chain such that it has desired stationary distribution PI. So that's the goal of this algorithm. Like you don't even know the distribution. Actually, sorry, you know the distribution, but you don't know the transition probabilities. You can still construct it. And then the Metropolis algorithm will actually provide this transition matrix. And so that is, it's gonna, and now I'm gonna describe the steps of the Metropolis algorithm. So it will provide a transition matrix that satisfies the detailed balance condition. Now, so let the chain be in a state Zi, and we propose to move to a state Zj according to some proposal probability. So we have a proposal probability, and it's up to us, this proposal. It's a random. And but it has to be chosen in such a way that you sample all possible states so that you have ergodicity. Now, you choose it, and then the next step, which is the main step of this very simple algorithm, but works in almost every case, is to say, well, I will accept this proposed probability with this probability, proposed state, next state with this probability. That is, you're gonna form this ratio here, and you're gonna see, is this larger than 1 or smaller than 1? And if it is larger than 1, you will accept it. If it is smaller than 1, you will not accept. Well, if it is smaller than 1, you will, sorry, the opposite. Yes, exactly. If it's larger than 1, you will accept it. That means the probability of acceptance will be 1. If it is smaller than 1, you will accept it with the probability that the ratio is. And and because you accept with probability, you know, it's a stochastic process. It's a stochastic algorithm. It could be, and very often is the case, that you don't accept the state. If you don't accept the state, you retain the previous state. That's it. And that's the whole thing. So you have the system in a certain state. You propose a new state, you accept it with this probability. If you accept it, you move to the new state. If you don't accept it, you remain in that state. And if you keep doing that, you're gonna evolve the matrix to the required stationary distribution, and so not the matrix, the chain. And now this is actually very, very easy to check that it works. So even a proof, one can say. So like without loss of generality, you can see later why it's without loss of generality. You can say, well, let me consider the case where this is true. If this is true, now I'm going to calculate the left-hand side of the detailed balance condition. You just calculate it and you get that. Well, for the opposite, the right-hand side, Pj, Pji, because now this is 1, it's just that, and they're equal. Obviously, if you have the opposite, if this one is not smaller, but greater, you're just going to reverse the indices, and it's still going to work. So this very simple algorithm actually gives you an algorithm to generate a Markov chain that satisfies the detailed balance condition. Then this means that the distribution is stationary, and if you deal with a physical system, the distribution, as I'm going to say next, is the Gibbs distribution or the Boltzmann distribution, and therefore you successfully simulated the physical system. That's how it works. So how do you simulate a physical system? Well, consider a physical system with n states and energy levels, En. And we use the Gibbs distribution, which states that the probability to be in a given state is e to the, it's this, it's e to the minus the energy of that state divided by the Boltzmann constant times time. So these are the entries in the stat sum that we have in statistical mechanics, in statistical physics. So, and the nice thing here is in this algorithm is that you only need the ratio of the stationary distribution. You don't need actually the overall normalization constant. The thing is, it's nice because you don't know it before you did the simulation, and all you need is the ratio of the probabilities, and this ratio of probabilities just depends on the difference of energy levels. And therefore, as long as you have a procedure to propose a new state of the system and calculate the change of energy, you can simulate the system. And this is why it's so widely used, this algorithm. Like, it is obviously an old algorithm, and there are many improvements of the algorithm, but they all use specifics of the system. So the moment you have some complicated system, almost certainly you will use the Metropolis-Hastings algorithm. It can be, of course, the details of how you propose new states. I mean, this can be, there are many different ways to do that, but the essence of the algorithm is this. Now, so it looks nice, and it is nice, and the nicest thing is that, and the strength of the algorithm is that the system can be in any state. So you start from any state, you evolve it, and you arrive at the answer. Eventually, well, you arrive at after many repetitions, you arrive at a chain that is in a stationary state and just fluctuates around this. Well, it just fluctuates with this transition probability of this stationary state, but this stationary distribution. But you pay a price for that, because if you have a very complicated system, the probability that your initial guess will be probable for that system is very low. And that means you start with something which is hugely improbable. Like there is, like, it's like if I want to simulate the molecules in this room, and I start with the condition that they're all now in my, in a glass of water, in a glass. And then you have to evolve the system, and the system has to evolve for quite a long time to forget the initial state. And why is that? Because starting from such improbable state and guessing another state, you generate huge differences in energy, and you actually accept with very low, practically zero probability. So if you want to actually evolve your system, your acceptance probability have to be sufficiently large, which means you have to evolve it very slightly. But if you evolve it very slightly, it's highly autocorrelated with the previous state, and it forgets very slowly the initial state. And that's why for a complicated system, a lot of time is wasted and lost to bring it into a thermal state. We call it, well, it's kind of like thermalization. It's called thermalization, this process. And so this, not only autocorrelation increases your statistical error, because it does, but it also makes it very slow to forget. And that's why this is this becomes problem when you have large size matrices. Computationally, you have to wait days for it to thermalize, and then you change something, you have to thermalize again. And so we were thinking with Denju, who is in the audience now, like, can this be improved in some way? And just to give you here example, this is simulation of a model with quartic interaction, matrix model with quartic interaction. And as you can see here an example of thermalization. So at the beginning, you start with some state here, and let me just, oh, okay, they killed. So you start with some initial state. And as you can see here, this is just one observable. You can think of it as the energy, if you wish, of the system. And as you can see, at the beginning, it just brings itself to a much more probable state. And then when you keep running it, you will never see the system actually going to that state. So this was hugely improbable state. And you needed a lot of time to reach here. And then after you're in the thermal phase, this is thermalized state of the system. This is how it looks like. And it oscillates around these points. It never goes here. So this was hugely improbable state at the beginning. And this is a very simple system, which takes very short time to simulate. Like for complicated systems, it's much more complicated. So therefore, there is a good reason, there is good incentive to want to improve that. And the way we propose to improve that, and is to use the generative adversarial neural networks. Now, they are very hot in, if you follow this line of research with artificial intelligence, because they're used to generate fake images. So this is the same techniques that are used to generate fake people. So they generate, you see a human face, but this human face belongs to no one. So the machine generates a fake human face, for example. And these are actually systems of neural networks that are good in simulating distribution. But that's what we want, right? And the way it works, the name adversarial comes because it has two components. It has a generator and discriminator. So you, at the beginning, you take your training set and you train the discriminator to be as good as possible to discriminate something as belonging to a certain state or not. In this case, could be something as being human face or being, like random noise or anything, but not human face. And once you train your discriminator to be perfect, then you train a generator that actually generates images and tries to trick the discriminator. It tries to trick the discriminator to generate something that passes for a human face. And then they train itself, the network, they compete, and the final state of this training process, a generator that is very good at tricking the discriminator. That means generating fake human faces. Now, what are images? Images are just, a matrix of pixels. So it was very naive, of course, to say, well, why don't we do that for matrices? And the reason why I'm saying naive is it's a bit of overkill to do exactly that. And I tried that. So what I did was I tried to learn the discriminator. It's the proper English to be used here, to learn it, So I tried to learn the discriminator, and I generated a lot of these states from here. And I generated states that are not from this simulation, but random states. And I tried to make the network, one neural network, classify them as belonging to that or not. And it wasn't working until I realized that I don't need the whole matrix, but just the eigenstates, because this matrix has it's a Hermitian matrix. It has n square components, but n square minus n components of it are actually due to gauge symmetry. And if you look at in the dynamics, these components, huge part of the components have dynamics that it's not important to the dynamics of the system. It's just the eigenvalues that are. And now if you start learning the discriminator to classify the eigenvalues of a random matrix and the matrix from this distribution, it's very quick. And the larger the matrix is, the better it is, because the eigenvalues of a matrix of size 20 already more or less follow slightly the distribution that these eigenvalues have in the large n limit. Well, it's not the large n limit that is important here. It is important that they're sampled from a distribution, but you have just n samples of them, and the larger n is, the closer the more information they have for the actual distribution. And the neural network is very good in actually capturing these differences in distribution. And now, and this is the most important part, to be able to actually train your discriminator to classify something as belonging to the thermalized state and not belonging to the thermalized state. And this I think is already, there is a proof of concept for that. Now, the next step is to do the generator. Not that it's so difficult, it's just, it is not useful to do that unless you have the first one. And then the idea is to now use this to improve the algorithm. Let me describe how. So the idea is to train the GAN to generate matrices from a given distribution using thermalized configuration for a given size of the matrix N. Now, then the next thing you do is now you actually, but how do you do that? So you actually make the GAN, you ask the GAN to generate 2N matrices of size 2N. Then you take the eigenvalues of the generated matrices and you undersample them. You take just N of them, and you compare them with these eigenvalues here of the classifier, and you train. Then in this way, you train your generator to generate something that can pass for a lower dimensional version of the thermalized. Well, to pass for thermalized N, thermalized state in the matrix model of size N, but it will be closer because the distribution, you know, like it converges rather fast with N. It will be already close enough to the actual thermalization distribution for 2N. And in this way, you can generate a 2N, and it doesn't have to be 2N, you know, it could be 1.5 times N, right? I'm just giving an example of N. And this allows you to actually use thermalized configuration for small n and to generate thermalized configuration for larger n. And it doesn't have to be exact, it just have to be close enough so that you skip this first expensive part of the thermalization. Yeah, and you can see this was a matrix model with quartic potential. It already scales as n to the power of 4, but more complicated models, especially if they have fermions, scale even with larger powers of n, I think, or they're more expensive anyway. And so being able to do that, who knows, if it works well enough, you may be able to do this 3n, you know, not 2n. And this is the idea. It is work under progress already. I could show some numbers, but I'm not going to show. But I'm just going to say that the classifier here for n equals 20 size matrix becomes perfect. Now, I don't know how general would that be, but for what I've tested, you can perfectly learn the discriminator to discriminate states from a given distribution. And then if this is now it all depends on the details, but if it's a very expensive for simulation system, it might be even useful to use the GANs to modify the proposal state of the Metropolis-Hastings algorithm, where you propose a new state. You're going to say, well, instead of taking the old state and evolving it, you know, slightly so that I don't generate a big change. Maybe because I'm doing this blindly, you know, I'm just blindly modifying it, and that's why I modify it slightly so that I don't violate the distribution too much. But what if I know a way to generate a new state from the distribution and offer it? Then I would lower significantly the autocorrelation. And it just has to be tried whether it will work. But another application is that you could probably use that to update for the update procedure of the Metropolis-Hastings algorithm. And this is what I've been playing with recently. Okay, so exactly 1 hour, I think. Thank you.
Okay. Are you done, Vesko?
Yes.
Okay, so let's thank Vesko for this very contentful talk. There is time for just one quick question, and it's actually already injury time because we're past 2 p.m. So some short question, if there is any.
May I ask? Thank you for your communication. How the 11 dimension appear? You have 11 dimension appear. We have Minkowski space, 4 dimensions, Calabi-Yau space, 6 dimension. This 11 dimension appear when we embed curved anti-de Sitter space to no.
No, the 11 dimension comes from this has to do with this dualities between string theory, the different string theory dualities, and type 2 A string theory can actually be obtained by dimensional reduction of 11-dimensional supergravity. That's where it comes from. It's this work by Witten, I think, that they have these 5 branches of string theory. And it's actually just mathematics. Like if you look at the classification of superalgebras, you can see the special role played by 11, 10-dimensional, etc. You can, if you look at the how are these called, the charges, yeah, that correspond to the Ramon fields. If you're not satisfied with the physics of it, you can think of it as just coming from the mathematics of super algebras.
Okay.
Okay, so let's thank Veselin once more, and I will just stop and restart recording briefly for technical reasons, and then we move on to our next talk.